Good morning, and welcome to this new episode of Control Systems 1. So in previous classes, we have started this cycle of developing geometric tools to understand what was going on with these transfer functions, these really important mathematical entities and control systems that relate the steady state values of inputs and outputs for linear time invariant systems. And it was maybe a tough journey, but we got 99% through it. And we looked into Bode plots, into Nyquist plots, and into the root locus as the different methods to assess what were the conditions, and particularly the stability of the closed loop system in a negative feedback loop by only doing considerations based on the open loop transfer function. So we saw that these methods were more or less complicated, but definitely they're very used, and each one has different, let's say, pros and cons depending on different situations. But these tools that we have looked into, we've used them for analysis up to now. That means let's determine for which values of k, and we're already imposing, so to speak, that the controller has a certain structure, that is, it's a proportional controller, to assess what is the stability of the closed loop system. Now, you might remember a few classes ago, towards the beginning of the course and maybe some other time throughout, we mentioned that the whole point of control systems is to achieve three main objectives in a specific order. First is to guarantee, of course, the stability of a system, because without stability, things blow up, right? So if things blow up, they break. Catastrophic outcome in a way or the other, and that's not desirable. So stability is the first concern of a controller. But then stability alone doesn't really tell the whole story, because stability is a property of the steady state. We know that eventually the system will tend towards something that is desirable. But what's going to happen in the meantime, right? So we have to care about performance as well. And performance can be intended as, for example, specifications in the transitory of the response. That is, that part of the output term that we kind of neglected up to now. And we said, okay, so this depends on the poles of the system, of the closed loop system. We care that it's stable, that the real parts are negative. But then we kind of left it at that. But actually, shaping where these poles are determines what are the properties of the response in the transient, so at the beginning. And another important characteristic of objective of control systems is that of guaranteeing robustness. So robustness is intended as something that relates to dealing with uncertainties, in particular uncertainties related to the plan, to the model of the system we want to control. An example of an uncertainty of a robustness problem would be, suppose you are driving a car down the road. Well, you want to make sure that the car responds to commands even if you, let's say, have too many people on board. So if the mass of the car has increased, right, because that changes the model of the system, you definitely don't want to design a controller that works exclusively for a certain value of the mass, but it should be able to handle some bounded variations in the parameters that characterize the system. So today, we are going to wrap up, let's say, the Nyquist plots by just doing one more example that tackles a particular corner case that we have not had the time to see last time. And then we will do two things. We will first introduce some, let's say, high-level measure of robustness. We won't go much more in the topic of robustness in this course because it's, let's say, it's a more, let's say, advanced set of things to know that you'll see in Control Systems 2 and maybe in other courses. And we will talk about performances and what does it mean to specify performances. If somebody comes to you, you're a control system engineer, says, okay, I want a system that is performant. So what does it mean, right? So how do we quantify performances? Sure, in properties of a transient response, but maybe even in, for example, capabilities of the system, the closed loop system, to handle disturbances or noises and things like this. So just a quick recap on some important, let's say, ideas that we've been throwing around in the last few classes. We are having in mind always a feedback system like this. A closed loop feedback control system with negative feedback means we sum up R and subtract the E part. And we look at different transfer functions between different signals in the system. And we said, well, the closed loop transfer function is there's this complementary sensitivity function that is, has the denominator that is very important. We've been playing around with this term for a while. It was the, let's say, focus of all these geometric methods we have been looking up to now. And we can notice that the closed loop poles are the solutions, that is the zeros, the roots. This is kind of confusing. Try to nail it once and for all and don't get confused again. So the zeros of an equation is a general term to say the values of the x or whatever it is that makes it zero, right? So the zeros of the denominator of the closed loop transfer functions are the poles of the system. And not to be confused with the zeros of the system that are the zeros of the numerator of the transfer function. It's a little bit of ugly terminology. So the solutions or the roots or the zeros of the denominator of this complementary sensitivity function are the poles of the closed loop system. And the zeros are identical to the poles of P of S, which is the plant. Now, we know that stability, asymptotic stability, is guaranteed if the real part of all the poles of the system are in the left-hand plane. That is, they have a negative real part. And we saw that the poles can have a real and imaginary part, and we typically associate the imaginary part with oscillations, and the real part with some time, let's say, scale properties. We'll recall this concept again later in this class. And so this is the setting, and what we have developed up to now is let's look at what happens to the poles of the closed loop transfer function when we play around with K. And so in particular, in last class, we looked at Bode plots, which are a way to look at the frequency response of a system. And they're characterized by these two graphs, the magnitude and the phase. And we saw that given an arbitrary complex transfer function, we can always break it down in some building blocks, constants, single terms, binomial terms. And we analyze the contributions of the magnitudes and the phases of these terms, doing some approximations in some cases, some asymptotic approximations that allow us to quickly sketch the frequency response of the transfer function, of the frequency response of the system, and provide some information. Why? Because the frequency response tells us, frequency by frequency, what is the steady state behavior of a system when a sinusoidal input is given. In particular, if we send a sinusoidal input in a linear time invariant system that is stable, and we wait for steady state, we will see that the output is a sinusoidal system, a sinusoidal signal in the same way, with a magnitude that is the magnitude of the input scaled by the magnitude of the transfer function at that specific frequency, and the phase is translated by the phase of the transfer function at that specific frequency. So today we will look at, again, one example on Nyquist plots to cover the case where we have poles on the imaginary axis, so purely imaginary poles, poles in zero, that we have not talked about before. And then we will continue towards talking about specifications, both in terms of robustness and of performance in the transient of the response. So this is just a wrap-up of previous class. We saw how to plot Nyquist diagrams. We saw how to do those with the help of Bode plots. We have never treated the case in which there are poles on the imaginary axis. The idea behind it is that, well, we cannot draw the D region anymore as we talked about. We have to kind of make some little kinks, we have to turn around the poles. But in practice, the takeaway is that when we have poles in 0, we have to close the Nyquist, the polar plot, to get the Nyquist plot, from the negative to the positive zeros of the frequencies by doing half circles that are clockwise. Kind of seems like a weird thing, but we can look at an example now. So suppose we have an open loop transfer function that is given by this thing here. So how do we proceed if we want to, for example, get an understanding of what the frequency response is, do the Nyquist diagram, and possibly even some consideration on stability in different cases? So, well, we looked at how to do this last time, but we can quickly redo an exercise. So the first thing we want to do is recast the transfer function in the Bode form, right? So we want to make each one of those terms be the same as what we analyzed. So having in particular the form, for example, of 1 plus tau s in these binomial terms. So here, of course, I'm being a little bit, let's say, exaggerated with the notations just to show the passages that I'm doing. The first part is the numerator. Well, we have to take a 10 out of it, and here it is. At the denominator, now we have a pole in 0 that we don't really have to touch, but this s minus 1, we want to put it in the form, sorry, 1 plus tau s, so we gather a minus 1 outside. So now, what terms do we have? We have this term up here, and these other terms at the denominator. So let's start with the numerator. We have 1 plus s tenths, so tau is equal to 1/10. So this means that 1 over tau, which is the breakout frequency, is 10. So I guess we have to specify these are the omega. This is where we are going to plot the magnitude in decibels of the frequency response. Here we're going to put the phase, and we're going to express it, for example, I don't know, in degrees or in radians. It's the same thing. So, okay, let's put the decades. We start, for example, here. This is 10 to the 0, so 1 radiant. The second, this is 10 to the 1. This is 10 to the second. This decade here is 10 to the minus 1. This is 10 to the minus 2. And of course, the corresponding in the top graph. So, any of you remember how this monomial terms work? Well, it's a monomial term at the numerator. It has a tau that is positive. So if I'm not mistaken, what happens is that we go and find the breakout frequency, which is 10. So it's this value here. And suppose that this here is 0 dBs, and this is 20 dBs, and this is minus 20 dBs. This is minus 40 and so on. So what are we going to do? We're going to go here, look at 0, and so look at 10 at 0 dBs. This is the breakout frequency. What happens is that this term will contribute with 0 magnitude up to here. We're doing an asymptotic approximation. This is not exactly what happens, but it's good enough for us to tell what is going on. And after that, it will start growing with with a slope with the 20 dBs per decade, which means 1 decade afterwards, we are at 20 dBs up here, and this grows up like this. Please correct me if I'm doing mistakes. Huh? So what about the phase instead? Well, the phase starts from a 0, so let's do what? Let's put 0 up here. So what are we going to do with this 0? Well, this is the breakout frequency. We look at 1 decade before and 1 decade after. So actually here I might have, well, we kind of need another decade, but it's going to be 0 up to here. And then at 1 decade before and 1 decade after, we have this linear behavior, and this is 90 degrees. correct? This is S plus 10. Actually, this is, just so that we don't forget, 1 plus S tenths, 1 plus S tenths. Okay, now let's look at the other terms. Now we've got S, or let's do 1 minus S, that is similar to the one before. So tau is equal to -1. This means 1 over the absolute value of tau is equal to 1. That's the breakout frequency, which is here. So let's change color. Maybe it's helpful. Let's do it in green. So this is the green part. Well, what are we going to do with this? Well, this is a term at the denominator now, right? So the contribution of the magnitude from, so the breakout frequency is 1, so it's 10 to the 0 here. So this goes to 0, 0, 0, 0 up to here. And then it starts going down with 20 dBs per decade, something like this. And what about the phase? Well, the phase, now this is a little bit, try not to get confused. So the phase is something that starts from 0 and ends up at pi half, 90 degrees. It's at the denominator, so it's actually minus 90 degrees, but the tau is negative, so we flip it over again, it's plus 90 degrees. So this goes from basically 0, 0, 0 up to 1 decade before the breakout frequency. 0, 0, 0, up here it goes here, connects like this, and then it's really ugly. And then it goes back at 90 degrees. Anybody disagree with this? And this is the 1 minus S term. No? Yes? Maybe? Okay. Now, let's look what happens with the S term. So the S term is, if you recall the Bode plots that we did last time, what happens? Well, it happens that it gives a contribution to the magnitude that is a slope of 20 dBs per decade that passes through 0. So this is a decade, these are 20 dBs, we need only 2 points to draw a line. It's going to be something like this. It's at the denominator, so the contribution of the magnitude decreases. Let's put S here. And what about the contribution of the phase? Well, the contribution of the phase is going to be minus 90 degrees, I think. Is this correct? Actually, I'm going to put it here to make it nice. And is this all? Are we done? Yes, no, maybe? This is kind of the mistake that can be done most often. Are we done or not? We actually did the same mistake when I was doing an example in class the other time. See, you're all on top of your Bode diagrams. Okay, note for, yes, sir. Very good point. Yes, we've got the constant. The constant itself is a term. And don't underestimate your constants because, let's see, blue. Because especially if they're negative, they have a very significant contribution of the phase. So we have the term k equals minus 10. So what we're going to do is add a contribution in the magnitude that is, let's say, k dBs, which is going to be, what is the 20 logarithm base 10 of minus 10. It's actually, sorry, of only 10. So this is KdB goes up here. It's going to be a contribution like this, equal at all frequencies. But the thing that is most important is that it's negative, which means this gives us a minus 180 degrees contribution to the phase at all frequencies. Okay, so now we have plotted the individual terms. What does that give us? It gives us that I have only yellow left, and this is unfortunate. But now what we have to do to get the frequency response of the whole transfer function is add each term frequency by frequency, right? So, okay, let's see what happens. Up to here, basically, do you see the yellow or is it really ugly? It's kind of ugly, right? Okay, so I'll do it in, let's say, black, just because. So we will go up to here. If you notice, basically there is the main contribution is given by this red term. So it's basically this red term translated above by some quantity of kdB. So up to here, it will go like this. And here we have these two terms, the red and the green, that will start contributing with a minus 20 dBs per decade. So up to here, which is 1 decade, we'll have minus 40 dBs per decade. So this means that roughly we end up here. And then there is this other term that starts contributing positive 20 dBs per decade with the minus 40 of the other side. So it goes down only at minus 20. Oops, this is not correct. It goes down at minus 20 dBs, okay? What about the phase instead? Well. So we've got these four terms. It's 0, 0, minus 270 is where we start from here. Then up to this point here, basically nothing happens. It's minus 270. Then up to this point here, we have a contribution given by this green term. So we go up. And then after this term here, up to here, we have two of these terms. So it goes up even more. Where does it end? So let's look at the final value directly because it's important. So we have a contribution of 90 degrees from here, plus 90. That's the black and the green term. Then we've got a minus 90 of the red and a minus 180 from the blue term. So if I'm not mistaken, this leads us to minus 90 at steady state. Okay, so a steady state, sorry, that doesn't mean anything, at high frequencies, okay? So, is this clear? Does it make any sense to you? No? I saw you were like kind of, I don't know. If you say it with a convinced enough tone, I could probably sell you anything, but anyways. So, okay, so how do we use this information to do the plot of the Nyquist diagram? Well, remember that the Nyquist diagram is a polar plot, so basically the further we are away from the origin, that is the magnitude, and the angle with respect to the real axis here is basically the phase. So you can imagine this is 0, this is minus 90 degrees, this is minus 180, this is minus 270. So let's look at the 0 frequency, so at very small frequency, we have an infinite basically contribution from the magnitude, means we're starting very distant from the origin. At what phase? At minus 270. So basically we start up here. This is omega 0 from plus, okay? Then what happens? Well, it happens that, look at the final Bode magnitude. Basically, it's always decreasing, okay? It's always decreasing, and at infinite frequency, it ends up having a minus infinite dB's magnitude, which is a complicated way of saying 0, right? So this will end up falling in the origin, this Nyquist plot. Okay, but from which direction, right? So let's look at the phase. The phase at steady state is, sorry, again with the steady state at high frequencies is what? Is we said minus 90, so minus 90 is here. So it means that we basically end up in 0 like this, and this is gonna be probably something like this, okay? So at every point in frequency, we are moving in this diagram, and distance from the origin decreases always, and then we end up in 0 at the right size. And then we can do the negative part by just taking the symmetric. So this is moving in this direction, and this is moving in this direction, okay? And this is omega from minus. Now, are we done? No, because there's a pole in 0, okay? So a pole in 0 means that we have to close the Nyquist plot from the minus to the plus with half circles in the clockwise direction. So something like this. Okay, so this is our Nyquist plot. Now, what are we going to do with this? Okay, this is all fun and dandy, but at the end of the day, what are we going to do with it? Now, if you remember Shima's class, it's very important where this plot is with respect to the critical point -1. So imagine there's many ways of seeing this. My favorite is to place the point -1 here. Let's look at all the possible cases, because what we're trying to analyze now is basically what happens to this Nyquist plot if we change the k, right? Please note that in all of these considerations that we've done up to now, we have not said anything about k. We just assumed k was 1. Okay, we didn't analyze it. So suppose that k were 0. If k were 0, what would happen to this whole game? Well, 0 times whatever it is, it's 0, right? So we wouldn't have anything. The Nyquist plot would just, yes. This thing here, this is the contribution of the pole in 0. It's like the point of this exercise. So when you have poles and zeros, you have to close the Nyquist diagram with a number of half circles in clockwise direction if you assume that we're moving counterclockwise with respect. So just take it as a rule of the Nyquist plot. Keep in mind, it's 1/2 circle for every pole in 0. So if you had 1/s², it would be 2 half circles, so a full circle and so on. So now imagine we have k that multiplies this transfer function that is 0. So now if we have 0 times something, it becomes a 0, so all this exercise collapses in a single point. So in that case, try to imagine shrinking all of this into a nice dot at 0. So where is the -1 point? Well, the -1 point would be at a long distance, right? It would be out here, correct? Now, if instead we are increasing k, there's going to be some values of k. At some point, as we increase k, we're magnifying the Nyquist plot. We'll get to a point where the -1 point is going to be in that circle. And instead, if we flip over the sign of k, we're going to have cases in which -1 is up here. So let's look at these cases one by one. So this, let's call this point here A. Let's call this point here 0. And this is case 1. So in case 1, basically what we are having is that k is basically smaller than a certain value, but is bigger than 0. In the second case here, we're basically saying that k is a big number because we are increasing. If we increase k a lot, then the Nyquist plot is going to be very big, so it's going to surpass the critical point. What is going to happen is that this means that k is bigger than ka. And in the third case, it's basically k less than 0. Does this make sense to you? Yes? Okay. Now, what does this tell us? Well, now we can apply the Nyquist criterion, which means now let's look at these 3 different cases and count the encirclements of the Nyquist plot around the critical point and compare them to the number of unstable open loop poles. And one way of doing it is we just take a direction and we count as +1 any counterclockwise encirclement, or let's say crossings of this line. In this case, we have a crossing in this direction, so this counts as a -1. Our system, how many open loop poles does it have? The unstable open loop poles does it have? Well, S-1 means the pole is S equal to 1. 1 is positive real part, it's an unstable open loop pole. So basically, in this case here, so the open loop unstable poles are in R1. In this case, we have -1 encirclement. So this means in this case, we have instability. For these values of k, we have instability. What about this central case here? Well, let's take any direction, for example, this one. Now we have one crossing in the counterclockwise direction, which gives a contribute of +1. So we've got +1 encirclement. We've got +1 open loop poles always. This means that in this case here, we have asymptotic stability. In this other case here, we can just take any random direction. We have no crossings. This is unstable. Right? Okay, now all this is fun, gives us some insight. But what is Ka, right? So how do we actually, so we touched upon this in last class, but how do we figure out what is the value of K such that this transition happens? Not because it's kind of important if you wanna design your system. Well, one thing we could do is try to get this in continuous mode, and one thing we could do is say, hey, but we have introduced an algebraic way to see when the roots of a polynomial change sign, right? In this case, what we care about, what we are saying, instability, stability, whatever it is, what really means is that the real part of the solutions, of the zeros, of the closed loop, of the denominator of the closed loop transfer function is the poles of the closed loop transfer function are flipping sign. So if we apply the Routh criterion to the denominator of the closed loop transfer function, we should be able to find the value of K such that the system transitions from stability to instability, which is going to be exactly the Ka we need. So how do we do this? Well, remember that what we need to do is study 1 plus Kps, which is the denominator of the open loop transfer function. This is 1 plus Ls, which is what we have up here. So 1 plus Ls is going to be 1 plus what? Plus, what's the form we have? We can put it. K, S plus 10, S minus 1. Doesn't, of course, matter at this point which form you use. So this means that the polynomial is S times S minus 1 plus K S plus 10 equal to 0. This means it's S squared plus what? Plus K minus 1S plus 10K equal to 0. If we apply the Routh criterion, what we need to do is make an isotable in which basically we start from the second degree, first degree 0. We put the coefficients of the every other term starting from the highest highest power. So it's 1 and 10K here. On the next line, you put the odd ones. So it's K minus 1, and we don't have another one. Please make sure if you do these exercises that you don't get tricked by the fact that there is a power missing. In this case, we have the square, we have the linear term, and the S is 0 here, so we're all good. So what our objective is completing the first column. What goes here? Well, it's, so suppose this, not suppose, this you can consider it at 0. So really what we should put here is the determinant of 1, 10K, K minus 1, 0 divided by minus K minus 1. If you don't remember this, just go check the Routh criterion. So when there's a 0 here, this becomes very easy because it's just basically the term up here. So this is 10K, and we have completed the first column. How do we use this? Well, we know that as long as there's no variations in signs in the first column, then we're good. So let's study the sign of these three terms. So as K varies, let's say this is 0. What is the sign of the first term, which is a 1? Well, 1 is positive regardless of the K. What about K minus 1? Well, if this is 1, then K minus 1 is going to be positive for K bigger than 1, and negative for all other values. This is K minus 1, and then for 10K, it's going to be positive for K bigger than 0. So what does this mean? It means that here we have one variation in sign, which is, it means instability. Here we have two variations in signs, which means instability. And here instead we have 0 variations in sign, which means asymptotic stability. So this means that Ka of the above exercise is equal to 1, okay? Now, I wanted to do this exercise both to show how those things happen with the poles in 0, but even because this idea of using the Routh criterion to, let's say, place the poles, it's something that we can leverage later. Okay, so as you see, depending on the values of K, we get different behaviors, right? And one can ask himself, well, what happens when there's this transition between stability and instability, right? Well, what happens is that if we consider, let's say, an open loop stable plant, so when the Nyquist plot has this kind of shape, well, the distance between, yes?
Can you show the example?
This one? This one? What's wrong with it? I'm sorry for the handwriting. I couldn't switch this, so it's going to be fixed in the second hour, but I'm really in an uncomfortable position now. Let me know when I can proceed. What is all of this? Man, where have you been at 20 minutes? This thing here? Okay, so basically, the Routh criterion tells us, build take your closed loop, the denominator of your closed loop transfer function, okay? Why? Because that means something to us from a control system's perspective, because we know that if the solutions, the roots, the zeros of the denominator of the closed loop transfer function have a positive or a negative real part, that means the stability or not of our closed loop system, okay, which is like primary objective of a controller. So what? So we look at the first column of the Routh table, and we have to check the variations in signs between the different terms as k varies. Why do we do that? Well, because we know from the previous, for example, considerations, that there are some values of k for which the system, closed loop system, is asymptotically stable, other values of k for which it's unstable. For an argument of continuity, there must be some transition values, no? And the transition value here is what we call Ka. But how do we find this Ka? Well, one way of doing it would be, well, just go and calculate the poles of the system, of the closed loop system, and you find the K for which you have all your real parts of your solutions that are negative. But okay, that's of course relatively easy even in this scenario because we have a simple, let's say, polynomial. But suppose you have 5 poles, 6 poles, 7 poles in your closed loop system, and good luck with finding the analytical solutions. You can use the Routh criterion. So here, all I'm doing is looking at the signs of each one of these terms. So term 1 has basically positive sign because 1 is a positive number for all values of k. It's a continuous line, okay? Continuous means positive. The second term is k minus 1. It means that for all values of k that are smaller than 1, that term, that factor, has a negative sign. For our k is bigger than 1, it has a positive 1, and so on. So if you had 32 terms there, you would just check the sign of each one of the terms. And then you would look at the variations in signs in the different regions. So this means that in the region from k equal from minus infinity to 0, you have one variation in sign. That means that there is at least one pole, one solution of that polynomial, which corresponds to the poles of our closed loop transfer function, that has a positive real part. That means for us that the system is unstable. What you are looking for is the zero variation regions, because the zero variation regions means that there is no variations, that the real parts are negative, and that is good for us. Okay, so we did 8 slides in an hour. I think it's a record. But anyways, so we saw that instability happens when the Nyquist plot transitions through the critical point, right, -1. And we saw that as k increases, the Nyquist plot basically becomes bigger, and at some point this transition happens because the Nyquist plot will cross the -1 point. So actually, if you think about it, the distance between the point at which the Nyquist plot crosses the real axis. So the magnitude of the open loop transfer function when the phase is equal to -180 degrees. The distance between that point and -1 basically tells us how much we can still crank up the gain before the system goes unstable. In other terms, if you want to imagine it in another way, it tells us how much could we be wrong about our assumptions on the plant? Suppose that we thought this was the plant, but actually the plant is this one, okay? Just because we got a bad modeling for any reason. It tells us what is the margin of gain, basically. What is the leeway we still have with the gain before the system goes unstable. This is a very common and, let's say, first measure of robustness of a system. The biggest your margin of gain, the more your system is robust. The more it can tolerate, let's say, variations, uncertainties in the plant model. Or another way of thinking it means you have still more space to increase your gain before the system goes unstable. So basically, you can see the math here. All you're saying is, okay, let's define this omega PC as the phase crossover frequency, which means the phase at the frequency at which the phase is equal to minus 180 degrees, because minus 180 degrees is this point here. So all we're saying is that this distance here is related to the gain margin. And then equivalently, if we just add a phase to the system, what we're doing is we're rotating the Nyquist plot. So letting the magnitude stay whatever it is, if we consider the intersection of the Nyquist plot with the critical circle, that is this point here, so the value of the phase when the magnitude is equal to 1, then the amount of lag, that is negative phase, we have to give to the system before the Nyquist plot crosses the 1 point, the critical point, the minus 1 point, that tells us what is, it's a quantity called the phase margin. And it's another very important quantity that characterizes the robustness of a system. It tells us basically how much more delay the system can handle before it goes unstable. So these two quantities, the gain margin and the phase margin, are powerful indicators of robustness of a system and are typically required specifications for a design. One could come to you and say, hey, design the system and it needs to have like a margin of, gain margin of at least 10 dBs, 20 dBs, whatever it is, and a phase margin of more than 45 degrees. Typical values are 90 degrees, but more than 60 degrees. The more you increase the margins, the more you want a design that is, let's say, conservative. It's gonna work even if stuff that you might have not considered in your design happens. So sometimes you'll see this other term, the stability margin, which is just the closest distance between the Nyquist plot and the critical point. That is basically a way to put together the phase margin and the gain margin in a single number. Now, these two values can be seen very easily on the Bode diagram, and this is an important step. So let's say especially when the plant doesn't have, let's say, funky terms, we can see where so how did we define the gain margin, for the example? The gain margin was, well, let's look at the point at which the phase crossover frequency. So let's look at the point in which the Nyquist plot has a phase of minus 180 degrees, okay? So this is the phase contribution. Suppose this blue thing down here is the phase contribution of a system. This is the point of the phase crossover frequency. Well, then in correspondence to this point, we go and check what is the magnitude in dBs of the system. And the distance from 0, this is the margin of gain. While the margin of phase, we have to look at this point here, which is the point at which the magnitude of the open loop transfer function has unit magnitude, which means it's 0 dBs. We call this this point here, the gain crossover frequency, or sometimes known as crossover frequency. If people tell you the crossover frequency, they intend the gain crossover frequency. And in correspondence of this, the distance between the phase of the system and minus 180 degrees, it's the margin of phase. Take a break, we can continue afterwards. Okay, so back to your seats. Okay, so we've introduced the margins. Margins are very nice. Take your seats, we've got lots to do. We have just introduced the margins of gain and the margin of frequency, and the margin of phase, which tell us how much we can increase the gain or how much lag we can add to the system before it goes unstable. These are nice because they are nice, some measures of robustness, which are typically given as specifications to the system. Now, guys, I'm ready when you are. So, it's good to have a positive gain margin, means there's margin for improving your gain. A negative phase margin means the closed loop system is unstable, and same consideration for your phase margins. Now, we have talked about stability. We have introduced some measures to characterize, to quantify the robustness of a system. Now let's talk about performance. So what does it mean for a system to be performant? Typically, performance is a big term, kind of encompasses many different things. We typically consider specifications that are given in the transient of the response. So something that has to do with the time response of the system. So a system that converges to its reference signal as quickly as possible and with minimum error, just intuitively, would be a very performant system, right? Then we introduce some other specification. A performance system is a system, for example, that manages to attenuate noise very well. Every time we measure something, or we will have some noise in this that is fed into the feedback loop. And noise is typically something that is nasty and has high frequency. And so a good performant control system tends to at least not amplify this noise, because it would end up disturbing everything. And a good system is something that rejects disturbances. So disturbance rejection, what is a disturbance? A disturbance is typically a signal that has low frequency, and a controller, a feedback system that rejects disturbance is a system that can recover quickly when some kinds of disturbances are inserted into the loop. Finally, another another important performance metric is the steady state error. That is, what is the difference between the values the system's output has at steady state when time has done its thing, and with respect to what the reference signal is. So remember that what we're doing here is now considering the fact that we have a plant, okay? A plant that is a function of S with its nice output, okay? And this output is something that we might choose because we decide to control the plant to feedback, and compare it with something that is the desirable values of this output, something we call the reference signal. We compute the difference between the reference signal and the Y, that is the difference between where we would like to be compared to where we actually are. And we call this difference the error, the tracking error. And we feed this error to something that we call a controller, which in general could be itself a dynamic controller, a function of S, although up to now we have just imagined this to be a proportional number, a K. This controller produces a signal that is the input to the system, so we will call it U, okay? So at this point, suppose C of S is K for now, so we just imagine this to be K. And, well, what is U? U is K times E, right? And what is Y? Well, Y is P times U. And this is P times K times E, right? So what is E? Well, E is equal to R minus Y. So this is R minus PKE. This means that E is equal to what? E is equal to 1 over 1 plus KP R, right? So this is the transfer function between the reference signal and the tracking error. Well, if we want to imagine, suppose that we have a reference signal that is, for some reason, a constant value that we want our system to track, okay? So as time increases, R is just a constant value. A 1, for example. Well, then what is the Y? How's the Y gonna look like? Oops. At steady state. Any suggestions? What do we know about our steady state response given a sinusoidal input, for example? Gain and exactly. So a constant input 1, what kind of sinusoid is that? Is it a sinusoid? Sure. Suppose you have, your input signal is E at the ST, right? These are all the sinusoids including. So, well, if we put S equal to 0, that's 1, right? So a constant signal is nothing but a 0 frequency sinusoid. Good enough? So it means that the output is going to respond to what? The output is going to be a sinusoid at the same frequency, so a constant value. But what is that value? Well, it's probably not going to be 1. It's going to be the value of the transfer function evaluated at that specific frequency. Let's suppose that, well, not suppose, here the transfer function is, so this, by the way, we called this before the sensitivity function. So if we have R that is equal to E at the ST with S equal to 0, then E at steady state is going to be equal to 1 over, let's say it's going to be S of 0 times E at the 0t, correct? Which is an ugly way of saying 1. So what is S0 evaluated? Does everybody agree with this? It's an old result we have derived. It's just like the constant is basically a sine wave with a 0 frequency. And so this means that the steady state error, that is the difference, no, we all agree that the error, Y would be exactly 1 if the error were 0, right? Because the error is defined as the difference between Y and R. So if we look at this case here, well, when is this steady state error equal to 0? It's given by that exact equation, P evaluated at a certain number is, so let's actually do a little bit more of a, P evaluated at a certain number, at 0 is something we can call, this is going to be a number, sorry. So when is the steady state error 0? 1 is a 1, we can't really do anything about it. 1 is a 1, we can't really do anything about it. Well, if this term here, let's call it, by the way, this is the open loop transfer function, L of 0. If this value here is very big, then the steady state error will decrease, right? Because we are increasing the denominator. If this term, but even if we increase this value a lot, we will never have a zero steady state error, right? Do you agree with this? Unless this L goes to infinity, but having an infinite gain is probably not a good idea, right? So what we've seen here, we understand that basically by, at least intuitively, by looking at this, we can say if we crank up the value of the open loop transfer function evaluated at the 0 frequency, if we make that a very big number, what we do is we can reduce the steady state error of a system to a constant input to some arbitrarily small number. But we really can never send it to 0. In order for the error to go to 0, we have to get a little creative. So let's look at this written in a little bit more of a formal way. So the transfer function between R and E which is the same as the transfer function between D and E in this case, but for now you can forget about the disturbances and the noises, is given by the sensitivity function here, okay, where L of S is the open loop transfer function, which is P times C. In this case, we consider C to be just any polynomial ratio of S. So if we send an input that is a constant, which is at E at the 0t, what we get is this as a steady state error. And the value of the open loop transfer function evaluated at 0 is actually a famous term. It's called the DC gain of a system, or sometimes the Bode gain. And it tells us what is the steady state error. I mean, it informs us what the steady state error is of a system when the input is of this kind. Now, suppose that we had 0 at a pole. If we want our steady state error to be equal to 0, if this is the equation, there's no other way but having a pole at in 0 of the open loop transfer function. Because if we were now to calculate the limit as S goes to 0 of L of S, if this L of S now it's a sum L of S divided by S, well, if S goes to 0, this term goes to infinity. If this term goes to infinity, then the whole denominator goes to infinity and the steady state error goes to 0. So this tells us something. It tells us that, okay, but here in the general case, if we look at a constant, well, then we see that we can reduce the steady state error by increasing the DC gain of our system, but we can't really make it to 0 unless we add a pole to the open loop system, a pole in 0. But what if instead we don't have a constant, but instead we have, for example, a ramp or a, let's say, these are called, let's say, ramps of higher order. This is a 0 order ramp. This is a 1 order ramp. It's a 2 order ramp. Basically, if we send as reference signals any signal of this class with m integer, so, well, what we get at steady state is exactly the same thing as before. That is the transfer function evaluated at that specific frequency times what? Times the input signal, right? So if this is E at the ST with S equal to 0, well, what is this? Well, a first order ramp this is a constant, this is a line, it's nothing but the integral of the above, right? If we integrate this, you get this. Then this is a parabola, it's just the integral of this. Now, if you remember, integrals are indicated by 1 over S. So as we increase the order of the ramp, basically what we're doing is we're integrating the 0 ramp m times. And so we can express the input signal as E at the ST over S to the power m. Now, there's different ways to imagine this. So if we look at this equation, this tells us everything there is to know about the steady state error. And there is a nice property that comes out of it. Typically, it is desirable. One specification that is given is we want your control system to have 0 steady state errors for this type of ramps, type 2 ramps, type 1 ramps. Actually, in practice, it's very common to have type 0 ramps in the sense that you want 0 steady state error to a constant input, but it's difficult to imagine situations in which it's important to have 0 steady error to a line or to a parabola. And maybe a steady state error that is less than some given value for higher order ramps. Now, we can imagine, so if m is the order of the ramp, we can imagine L of S to have a number of poles in 0. Let's say we have, we isolate p poles in 0 from L of S. And, well, this then becomes the limit for S that goes to 0 of what? Of V at the ST over, let's say, S to the M plus S to the M minus P L of S, where L of S in this case is considered not to have poles and zeros because we just removed them for showing this case. Now, if M, we can basically generalize what we said before. If M is equal to P, then what we get is, what do we get? we get that as the limit goes to 0, then E at the ST goes to 1, M is equal to P, so this term here goes to 1, and as S goes to 0, this term will go to 0, and we will have a steady state error that is equal to 1 over 1 plus the Bode gain if M is equal to 1, or 1 over the K Bode gain if M is bigger than 1. What if M is bigger or smaller than P instead? So basically, what if we have poles in 0 in the open loop transfer function, L of S, that are bigger or smaller than the type of the reference signal that we're sending in? Well, we could just do the math here and do considerations on the orders of infinitesimal things of the different S terms, but it's intuitive to just think about it this way. Well, if we have, think about the constant input. If we have no poles in 0, well, then there is we just saw that regardless of how big your Bode gain of the system is, there's always going to be a steady state error. So for higher order ramps that are the integral of this, if you integrate a small error, you will have just in time a diverging error. So if the order of the ramp of the reference signal, M, is bigger than the numbers of poles in 0 you have on your open loop function, then there's going to be an infinite steady state error. On the opposite, if you have more poles in 0 than the order of the ramp in your open loop transfer function, you'll have a steady state error that goes to 0. I encourage you to just go find these conclusions by playing around with M and P in this equation. So all this can be summarized nicely in a table. And don't ask me why they're called system types, but basically this table, this is if you have a reference signal that is a ramp of order M, this means a constant or a line or a parabola or whatever. Let me remove this for future generations. But anyways, so if you have these kinds of reference signals, then if your system is of type equal in number to the order of the ramp, you have a constant steady state error. So the type is nothing but the numbers of poles in 0 of your open loop transfer function. Remember that the open loop transfer function is given by the plant you want to control times the controller you get to design. So suppose we were asked by someone, you have to design a controller such that this plant has 0 steady state error to a ramp, okay? So a ramp is M equals 1. It means 0 steady state error. It means we need to, this is the input, we want 0 steady state error. Our system needs to be at least type 2. Type 2, it means that this term here needs to have at least 2 poles in 0. But, so these poles in 0 don't really matter if they come from the controller or they come from the plant, as long as the open loop part has 2 poles in 0. So part of the design process is the first thing you do is you guarantee steady state error by adding the numbers of poles and zeros that you need to your controller for the plant to showcase the behavior that is desired. So typically the first step when you design a controller is you say, okay, let's consider a preliminary controller C of S. Let's say our final C of S is going to be C1 of S times C2 of S, blah, 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 Cn of S. Okay, so we can start by the first one and we say, okay, the first term is going to be some K1 over S to the power P, okay? And you choose P such that you get your you match your steady state error specification, whatever is given to you. And then you choose K, so you basically choose P such that you get 0 steady state error for all the input types, for the input ramps of some order. And then you can play around with the K1 so that you change the Bode gain in order to bound the steady state error of the specific M that you care for under a given value. And this would be the first step of the control over design. There's no other way to deal with steady state errors, okay? So if in plain English, if somebody comes to you and says, hey, I want you to give me 0 steady state error to a constant reference signal, that means your system needs to have, what is that? 1 pole in 0, needs to have an integrator. And if you think about it, that's kind of obvious, no? So we said that if you don't have pulling 0, then your system has a constant steady state error. Well, but if you look at the feedback loop, the only way for which the controller can actually know what is going on and actually do something about it is if the error is different from 0. Now, the error informs the control action because it tells us how distant we are from where we should be. So if you have a constant steady state error, but you integrate that steady state error, then that increases the, it gives direct information to the controller that it needs to take action in order to reduce it. So integrating a constant value will let us eventually drive the steady state error to 0. So yes, this is pretty straightforward, and it's all there is to say about steady state errors. Just make sure you add poles and zeros of the right number such that you get 0 steady state errors for all the ramps that are of order lower than your poles and 0, and so on. Of course, this doesn't tell us what is the steady state error to any kind of signal, right? It only talks about these types of ramps. So we talked about the steady state values. Now, how about what other kind of performance specifications are typically given? Well, one thing that is relevant is how the system behaves in the transient response. It is before it gets to steady state. And what is typical is basically defining the time domain, the performance specifications as if the system were a second order system. Okay, so it had 2 poles. And you can say, well, but the systems may have any number of poles. Yes, sure, but as we will see later, there are ways to nearly always approximate the behavior of the system as if it were, let's say, governed by the so-called dominant poles. But so suppose for now that our system behaves like a second order system. A second order system will have, it might have, in the general case, complex conjugate poles. So this will drive an oscillatory response. Suppose that we're sending an input that is a step signal. Okay, then we define as the rise time the amount of time it takes for the system to hit for the first time the let's say the reference signal, or at least some bound around the reference signal. This bound can be arbitrarily chosen. It can be 2%. It can be 5%. It can be whatever you want. So it's not like whatever you want, but it's different conventions. So now we're entering a domain where there's approximations, and basically you'll find the different definitions on every textbook you look at. But the rise time is defined as how long does the system output take to reach the reference signal for the first time. Doesn't mean it settles there, it just means it hits it. It's typically not a very important or a very meaningful time domain specification. One that might be, yes? It does. It does. The rise time is, okay, you can find it defined in different ways, but the fundamental idea is how long does it take for the system to reach for the first time a value around very close to your reference signal. Another performance metric that might be more relevant is the overshoot. The overshoot basically tells us it's typically expressed in percentages of the steady state value, and it tells us what is the biggest distance from the reference that the response will take, and this might be relevant or in case of specific systems. To imagine, like, I guess the simplest example is the door. If you let it go, how much does it flip over to the other side? You want to make sure that overshoot is not too big, otherwise you might hurt somebody that is walking in the back, right? Another important value is the settling time. The settling time is basically the value for which the system's response is contained within a bound around the reference and never leaves anymore. Okay, so this can again be defined arbitrarily depending on how big this region is. But the idea is once the settling time defines a sort of convergence, once the output is within the bound around the reference and we'll never get out of it again, that's the settling time. So We've seen before that if we have a second order system, we can express it in this familiar way, the transfer function, which yields a system output that has this form. So it's basically the steady state value scaled by this exponential term that is a function of the poles and of the poles. So the real and imaginary parts contribute to the sigma and omega, which are the basically real and imaginary part of the poles, and are related to omega n and the zeta, which we call the natural frequency and the damping of the second order system in this way. So, well, it's maybe worth recalling that given the position of these poles, if we have a second order system, this is the real axis and this is the imaginary one. Well, you remember we did this graph a while back for all the different positions. Now, so anything that is here means that if your poles are anywhere in the right-hand plane, means your system goes unstable. So when we can't even talk about all of this, otherwise the system will never converge, so it doesn't make sense. But suppose we have our poles that are here, right? So this this distance from the origin is going to be the omega n, and this angle here is going to be related to the damping zeta. If you see so the transfer function is equal to omega n square, s square plus 2 zeta omega n s plus omega n square. If you go calculate S12, this is what? Zeta omega n plus minus omega n zeta square minus 1 root, right? So this means that when zeta is equal to 1, what you get is a purely real response. Zeta is equal to 0, you get a purely imaginary response. And basically, as you move in different directions here, you get an increasing zeta, increasing damping. So why is this important? Because if you think about it, so if you recall, suppose we had poles here, okay? Let's pick a direction like this one. If we had poles here, this meant that our system response would have a decaying component that is only function of the real part, and then an oscillatory behavior that is a function of the imaginary part. And so let's suppose we have a full purely real poles. Well, then moving in this direction of a line means that the time response of the system is affected, but not the shape, in the sense that this having a very, very small, or actually big, in this case, in magnitude, negative real pole would mean that the response converges very quickly. Here, that the response converges less quickly if you had it here, right? But doesn't change the shape of it. If instead we just select one, let's say, real value, if we were, for example, here, we would have this shape. If we had a pole, for example, here, well, we would always have a faster convergence and the oscillations. But if we were to move on this line, we would get oscillations that are slower or faster, basically. So basically, this tells us that natural frequencies and the damping can affect the shape and the response and the time response of the system in different ways. And thanks to these, this is really ugly, but I have to, every control student has to go through this, and you don't have to take it as it is. So there are these analytical approximative, let's say, relationships that relate the performance metrics that we defined before with the natural frequencies, and the damping of our response. And I will not get into the derivation of this. You have them on the textbook. You can go and see them, and there's somewhat a degree of variability between different textbooks you find. But the fundamental idea is that the rise time depends primarily on the frequency of the system. And this is kind of intuitive. if you see now, the response of the system is dominated by this cosine omega t. So it will kind of be intuitive to imagine that, well, this is the point where the phase is equal to pi. This is the point where the phase is equal to 0. Well, here in the middle, it's going to be a function of course, the frequency and omega pi half. So the rising time depends by the frequency of the poles. The peak time depends again on the frequency. The overshoot, so you don't need to know these equations in the sense that you have to understand what influences the different parameters, and then you will always refer to them. But for example, for the overshoot, we can see that the overshoot is something that has to do exclusively with the shape of the response. In fact, it depends only on the damping. It doesn't depend on the natural frequency. It doesn't matter how much to the left of the left-hand plane you move your poles. It matters what's the direction with respect to the imaginary axis. The settling time is a function of instead the real part, because the bigger in magnitude the real part of your poles of the closed-loop transfer function, the quicker the convergence is. Please note that this, of course, is all related to second-order systems, right? If instead we had a first-order system, we couldn't be defining many of these terms because there would be no oscillations in the first-order system's response. But still, so you wouldn't have an overshoot, for example, but still you would have a rising time and a settling time, which would be basically the same thing. So, but really, there is no guarantee that a system will always have only two poles, right? So what we do is we make this dominant pole approximation. So it is customary to say that, well, a system can, at least as far as the specifications, the time domain specifications are given, to say, well, let's just give the specification as if it were a second order system. And what we do is we look at this dominant pole approximation. And so you might recall that the response of a system is given by the weighted combination of these terms that depend on the poles and on the residuals, right? And if you recall a few classes ago, where the poles are the negative real parts of the closed loop transfer function, if we're looking at the closed loop transfer function, and the residuals instead are affected by the zeros of the system, right? So these are a bunch of exponentials. And the way the dominant pole approximation works is that you basically neglect all those terms that decay faster. Because if they decay faster, it means that in a shorter time, they will no longer be of concern because they've decayed. So for example, if we had the three poles in a system, well, actually, we're going to see the examples later. But the idea is that since the output can be expressed as a sum of exponentials, the exponentials that have the biggest exponents, and here we're all assuming that the system is stable, so we're all talking negative real parts, okay? But the bigger the negative real part, the quicker the exponential will go to zero, so the rest relevant it will be in the let's say long term for the system. So what we do is we neglect all the faster, the modes that converge more quickly, and keep the slower ones, the ones that are closer to zero. There's an exception to this when the zeros are very close to the poles, because if you remember, when you get a zero that is very close to the pole, that affects the residual. So while we might have some terms that decay very slowly, but if their residual is very tiny, well, overall the effect of that term wouldn't be significant, because the residual, that is the weight of that term, is very small. So in that case, you wouldn't keep it as a dominant pole. So, but as general rule, you go and choose dominant poles. Suppose you have a system that has two poles here and two here. Well, you choose these ones because they're the slower ones, the ones that decay more slowly, because they have a negative real part that is smaller in magnitude than the other ones. Here are a few examples. So in this case, you have a third order system, and as you see, there is a pole in -5, and these other two poles are in -1. That's the real part, at least. So the dominant pole approximation, so the answer, the response of the system, can you see it, would be the blue line. And if we just say, okay, neglect the poles that converge more quickly, that is the one that has, of course, the pole with a negative, with the real part that is bigger, magnitude. We just keep the other two poles. Of course, we have to adjust the gain in such a way that the Bode gain of the system is the same. Basically here, what you do is you take the 5 out, and it would be 5, 1, and then 130 divided by 5 would be 26. You get a behavior that is the red line that is, of course, different from the actual response because it's an approximation, but it's qualitatively similar, right? So the time domain specifications would be given with respect to this dominant pole approximation. Suppose instead you have a slightly different system where the dominant poles are the complex conjugate ones. Well, sorry, in this case, the complex conjugate ones are faster than the other pole because they have the closest one to the origin. In this case, you have these two here and one here. So you can actually do a dominant pole approximation that is a first order one, not even a second one, because you can remove directly these two. And you would get, in fact, a behavior that is very, very similar. If you see the blue and the red line, it's basically nearly impossible to tell the difference. And of course, there is an exception when there is a zero that is very close to a pole, because in this case, the residual associated with that term would be smaller. So this term wouldn't be contributing as much anyways. So you can imagine as if these kind of neglected themselves, and the dominant pole approximation would conserve the poles that are less fast in this case. And as you see, the responses are very similar. So thanks to this, we can give some specifications on the performance of the system in terms of transient response and steady state response, thinking about it as a second order system. What is really important to keep in mind is that the settling time is basically how long before your system is where it needs to go. It's kind of important. And it really is influenced mostly by the real part of your poles. The overshoot instead is what is the maximum, let's say, error you're going to do before you get to where you want to be. And it's mainly affected by the damping. And the rise time, again, is affected by the frequency, but is not the most, let's say, useful of time domain specifications. Of course, it's very nice to use the root locus when you want to define or design a controller that is based on time specifications from given time domain specifications, because basically it becomes an exercise of placing the poles in the right part of the plane. So somebody could come to you and say, I want your system to have a rise time that is, or a settling time that is smaller than 10 seconds and an overshoot that is less than 3%, okay, or whatever it is. So this just means, through the analytical approximations that we saw before, rise time is nothing but something that translates on this value here, and overshoot is nothing but a given value of zeta. So all the combination of poles that are in this region here of the plane would be solutions to those specifications. And we will see probably in an exercise session or some other time that it's very straightforward to use the Routh criterion, for example, to place your poles in specific regions of the plane. So the next important concept is that instead of defining performances in the frequency domain. So here we're thinking mostly about disturbance rejection and the noise attenuation. So always think of noise as something that is high frequency, bigger than 100 hertz, for example, and disturbances as something that is low frequency, so up to 10 hertz, for example. And so if you recall, we saw that the different signals, for example, R2E was, or the transfer function between these two signals was the sensitivity function. For example, R2I, it was the complementary sensitivity function. And we showed a few classes ago that the transfer function, the complementary sensitivity function, the complementary sensitivity function, the sensitivity function, as the name suggests, are complementary at every value of frequency. That means if you do t plus s of s, you get 1. So while it is desirable to have both properties, that is disturbance rejection and noise attenuation at every point in frequency, it is fundamentally impossible, because having a, let's say, good, having, for example, a good disturbance attenuation means having a what? So if the transfer function between the disturbance and the error, for example, so given a disturbance, how much does our output miss the reference signal is given by the sensitivity function. So for example, we would like the sensitivity function to be small at that point, but this, the two constraints, the two, let's say, specifications cannot be applied at the same points in frequency. So this is a conundrum, it's a problem, it's arguably the biggest problem that is around, and it's solved by simply separating the problems in different frequency ranges. That is, observing that disturbances and noises are acting upon different frequency ranges. So we satisfy the constraint of T of S plus S of S in low frequencies in a way that the disturbance part is dominating, while at high frequencies, we can make sure that the part we're interested in, and we'll go into details of this later, is the one related to the noise. So what does this mean? Now, let's look at, so the sensitivity function is what? Is the transfer function from R to D. So it's the transfer function from the reference or from the output disturbance to the error, okay? So we want, if we want disturbance rejection, it means we want the transfer function from the disturbance to the reference or to E to be very small. So if we want S to be very small, it means the magnitude of S has to be very small, much smaller than 1, okay? So since there is this constraint, if S is much smaller than 1, it means that T has to be around 1 at low frequencies, okay? Well, if we want to have noise rejection, it means that the transfer function between the noise and the reference has to be, the noise and the error, for example, has to be very small. And this is a constraint on the complementary sensitivity function, which would mean, therefore, that since this transfer function is regulated by T of S, it means we want this to be very, very small at some frequencies. Of course, these two things cannot happen at the same time, because if T of S is 0.01, then S has to be whatever it is to get to 1. It can't be 0.01 as well. So, but we can say, well, we can make this small just at a different set of frequencies, at different values of S. And so we only have 1 minute, so I will make you go through these 1 and 2 slides on your own that explain exactly what this is, because this is arguably the most important graph of all times. And it tells us, well, in order to obtain good, I am sorry, I need to, but it's relatively simple equations. Give me 1 minute, please, and I'll explain you this. Disturbance rejection means that the open loop transfer function has to be big at low frequencies. It is possible to translate the constraints on S and T to the open loop transfer function L. And so a typical specification is somebody that comes to you and says, hey, I want your open loop transfer function to be bigger than some obstacle, than some omega 1 that is user defined, some lower bound at low frequencies. This means that disturbances are going to be rejected up to some frequency value. Well, to remove noise, instead, you want to have the open loop transfer function to be very, very small at high frequencies. This means under some function, some constraint omega-2 that might be given to you or not. Say, I want a noise attenuation that is of 1%. Okay, so you shape the omega-2 in that way. In the middle, you want to choose your gain crossover frequency in a way such that, as we saw for the main gain margins and the phase margins, this value, the value at which the open loop transfer function crosses the unity value, the 0 dBs, this is related both to the ability of the system to track faster signals or and to robustness. So we can maybe go through this again next time, but the most important thing to say is that basically we could finish the course here, because everything that we're going to do later is just ways to shape the frequency domain response in order to avoid these different obstacles at different frequencies, because that is what determines both the performance, the stability, and the robustness of a closed loop system. Thank you very much.